Welcome back to the deep dive. So today we are jumping straight into a substance that honestly sounds like it's straight out of a horror movie, not a chemistry lab.
Mm-hmm. It's one of those things that really challenges your basic common sense about how materials are supposed to work.
We're talking about a chemical that just it completely redraws the lines.
It really does.
Yeah.
And it's a perfect topic for a deep dive because it's the ultimate paradox. It's unbelievably dangerous, yet at the same time, it's completely essential for, well, for the world we live in today.
Right. We're talking about hydrofluoric acid, HF. And for anyone who's even, done a quick search on this, the first thing that jumps out from all the source material is it's simple.
That it dissolves glass?
It dissolves glass, not just etches it a little, but treats it like you're pouring hot water on sugar.
Exactly. And glass is silicon dioxide,
Yeah.
It's the material we count on to be stable and non-reactive.
Right.
But HF just doesn't play by those rules.
So that's our mission for today.
Yeah, we need to go beyond that headline. We're going
Yes.
to unpack the mechanics of how it does that, why it's so uniquely dangerous to people, and then the big question, why we absolutely need it for the screen you're probably looking at right now.
Okay, let's start there. The big question. If I had a vial of pure hydrofluoric acid and, say, put it in a glass cup, what actually happens? Does the cup just melt?
It's not really melting in the way you'd think, and it's not instantaneous. The process is a lot more strategic, you could say.
Okay.
Most strong acids, your hydrochloric, your sulfuric acid, they can burn your skin, strip paint, but they can't touch glass.
Right, because the glass is just too stable.
The bonds are just too strong. Glass is mostly silica. That's silicon dioxide, aside too. And it's built on these incredibly stable covalent bonds. Regular acids just can't break them down.
So they just sit there.
Pretty much. But here's where HF gets weird, and this is the real insight from the sources. Chemically speaking, hydrofluoric acid is actually a pretty weak acid.
Wait, hold on. A weak acid dissolves glass? That seems completely backward.
It is. And it's the most important detail. Its power doesn't come from being a strong acid in the classic sense. It comes from the fluoride ion, the F ion.
Okay, so what's special about the fluoride ion?
It is extremely reactive, and it has this almost magnetic attraction to one thing in particular, silicon atoms.
Ah, so it's not brute force. It's like a targeted chemical attack.
It's a chemical assassination. That's the key. The fluoride ion gets into the glass structure and literally rips the silicon atoms right out of that stable network.
So it's not just scratching the surface, it's breaking the fundamental bonds inside.
It's completely deconstructing it. When the fluoride binds to the silicon, it creates a whole new compound, silicon tetrafluoride.
And what's that? What does it look like?
Well, it's a gas or a liquid, so you're literally transforming solid, stable glass into something that just evaporates or dissolves away.
So what would you see?
The sources describe it as really unsettling. You'd see a hole start to form. Then it would just expand, and the glass around it would lose all its structure, turning into this kind of chemical mud.
So its unique power comes from that very specific love for silicon, not just general corrosiveness.
That selectivity is everything. And it's what makes it so useful and so terrifying, which takes us right to what happens when it touches a person.
Yeah, let's go there. Human contact.
Yeah.
If this stuff can disassemble glass, what on earth happens if a drop touches your skin? I'm picturing an immediate horrible burn.
That's the terrifying part. It's not like that at all.
Yeah.
This is why some medical professionals call it the silent killer.
The silent killer?
Yeah. Because the HF molecule is so small and it has no electrical charge, it can pass through skin and tissue incredibly fast, way faster than other acids that would cause an immediate painful surface burn.
So you're saying the danger is that you don't feel it right away?
Precisely. For the first 5 minutes, maybe even longer depending on the concentration, the victim feels almost nothing, no pain.
But it's still doing damage.
It's doing incredible damage.
Yeah.
While the person has no idea, the acid is moving deep past the skin, through the tissue, and it's heading for the bone.
It just bypasses all your body's alarm systems.
Yeah.
So once it's inside, what's its target then?
Calcium. Just like it hunted for silicon in the glass, inside your body, the fluoride ion relentlessly seeks out and binds to your body's calcium and magnesium ions.
So it's basically stealing the body's calcium.
It's shackling it. That's a good way to put it. It pulls the calcium out of your system where it's desperately needed for, everything.
Nerve function, muscles.
And most critically, your heart rhythm. By locking up all the available calcium, HF exposure causes something called hypocalcemia. That can lead to systemic failure, nerve damage, and very quickly, a fatal cardiac arrest.
That is it's genuinely frightening, especially that delay. That 5 minutes or more where you think you're fine.
I mean, just washing it off isn't enough. You're already fighting a chemical reaction deep inside your body.
So what do you even do?
It becomes a race against time. First aid teams have to immediately apply something called calcium gluconate gel.
To give the fluoride something else to attack.
Exactly. You're trying to intercept it. You flood the area with a different source of calcium, hoping the fluoride ions bind to that instead of calcium in your bones and your blood.
It's an extraordinary problem that demands an extraordinary solution.
A very specific chemical threat that requires a very specific chemical defense.
Okay. Which brings us to the big paradox here. We have a substance that can dissolve its own container and can silently kill a person from the inside out. Why? Why would we use this? Why is this mobile crime, as one source put it, so necessary?
Because that exact same targeted, relentless attack on silicon is what makes it completely irreplaceable in the modern world.
Okay, so let's get specific. What does it do in electronics that another safer chemical can't?
It's all about precision.
Yeah.
Extreme precision at a microscopic level. Think about the microchips in your phone. They're built in layers with silicon and silicon dioxide.
Right.
To create those impossibly tiny circuits, manufacturers have to carve away layers of the silicon dioxide, but without damaging the delicate silicon underneath.
They need a chemical scalpel.
The perfect chemical scalpel. And HF is the only thing that can selectively and reliably eat away the silicon dioxide without destroying the pure silicon right below it.
Yeah.
Any other powerful chemical would just destroy everything.
So its specific appetite is actually its greatest strength in manufacturing.
It allows engineers to sculpt features that are literally just a few atoms wide. It's not just cleaning the chips. It's fundamental to building the very structure of a modern processor.
And it's used everywhere.
Everywhere. Preparing the glass for your phone screen to get that perfect finish, manufacturing the microchips that power, well, everything. It's also used in processing really high-grade metals.
So the foundation of all this convenience, my phone, my laptop, it all rests on a substance that demands absolute total respect for its potential danger.
The sources make that crystal clear. Without industrial-scale hydrofluoric acid, we essentially couldn't make high-resolution screens or the dense microchips that define our lives today. We'd be set back decades.
So we come full circle. The thing that scares you is also the thing that serves you. It's like fire. It can burn you horribly, but it also cooks your food.
That's a great analogy. It's this incredibly powerful force that we've learned to handle with extreme care because we have to.
It really makes you think about the trade-offs, doesn't it? The hidden foundations of our sleek digital world.
It does. We rarely consider that the smooth piece of glass in our hands only exists because of a substance capable of such unique and silent destruction. It's a testament to the incredible balancing act of modern chemistry.
A powerful reminder that our most advanced tools often come from harnessing nature's most extreme capabilities.
Indeed. So the next time you're swiping on that flawless screen, maybe take a second to think about the power it took to create it. And maybe observe any glass dissolution from a very safe distance.